Okay, so we ended the last video with these two equations. This one relates the force on an object to its motion. So force tends to change the velocity of something if there's an unbalanced force. But the amount of acceleration you get, the amount of velocity change, is dependent on the mass, which we call inertia, which we call resistance to change, resistance to acceleration, or resistance to change in velocity. Over on the torque side, torque will tend to give us an angular acceleration. It will tend to change, either speed up or slow down a spinning object. But how much it speeds up or slows down depends on the rotational inertia. So this is what we want to talk about. So remember this. This is what we call rotational inertia. Another widely used term, even more common maybe than rotational inertia, which I prefer, is moment of inertia. So these things mean the same thing, and they refer to an object's resistance to being rotated faster or rotated slower. That's what we call rotational inertia, and that's what we want to learn how to calculate. Okay, let's start with this. This is a rod. Those are just tick marks. This is a thin rod that's 1 meter long. And I have two 1 kilogram slugs that I can put anywhere on the rod. So in the first case, I put the two 1 kilogram slugs at 10 centimeters from the center of the rod. Then I take two 1 kilogram slugs and put them 30 centimeters from the center of the rod. And then I put the two slugs all the way out 50 centimeters from the center of the rod. And then you grab the rod in the middle and you twist it back and forth. You can kind of feel its inertia, right? Like you can feel the inertia if you have a ball, a steel ball, and you don't know whether it's solid or empty. You take it and you can just kind of shake it and feel it. So this, by twisting, we can feel the inertia, how difficult it is to twist, how it resists being twisted. So obviously, or maybe it's not obvious, twisting this one will be relatively easy compared to this, and this is going to be harder to twist. And unfortunately, we're not in class. I have this gadget which demonstrates this. So what we want to be able to do is we want to calculate inertia for these simple situations. And I'm going to pause the video. So here's our equation for inertia. I'm not going to derive it, but the inertia of any point mass, that means a small mass, we'll have to deal with a disc or a rod or something that's big. But this is like a point, it's a small mass, and so its inertia will be the mass, and obviously the distance, that's the r, the distance from the axis to the mass. So r for this mass is 10 centimeters, r for this mass is 30 centimeters, and r for this mass is 50 centimeters, and so as the r gets bigger, the inertia gets bigger. Of course, it does depend on the mass, but it also depends on the placement of the mass. Now, if you have more than one mass, you need to add all the masses together. In other words, the inertia of this situation is the inertia of the two added together. And later on, we'll account for the inertia of the rod. Here we're just saying, oh, the rod is thin, it has negligible mass. We're ignoring it. But later on, we'll learn how to deal with the rod in case it's not negligible mass. And in that case, you would sum up the inertia of the mass and the rod. But for these three examples, you can start practicing now. Ignoring the inertia of the rods, just the inertia of the two masses, calculate the total inertia of A, the total inertia of B, and the total inertia of C. So pause the video and do that. Okay, here you go. So we have the first one. So we have mass 1 times its distance, remember, not radius, distance from the axis to the mass. and that was 10 centimeters, so 0.1 meters. I have to square it, and there's another one. So when I do this, I get 0.02 kilogram meters squared. Just to make that easier to read, I'm going to put a 10 to the minus 3. So 20 times 10 to the minus 3 kilogram meters squared. Those are the units of rotational inertia, kilogram meters squared. When I do this one, these are equal, right? So I'm just going to multiply one of them. The 1 times the 3, that's the 30 centimeters. Whoops, that's cubed. That's supposed to be squared. And then I'm going to multiply by 2 rather than do it twice and add it. And I get 0.18 or 180 kilograms. Now notice, this is like 90 times bigger. It's hugely bigger. 9 times bigger than this one. So as we move the masses out, the inertia goes up very fast because it depends on the distance squared. And by the time we get them all the way to the end, the distance now is from the center to the mass is 0.5. So 1 times 0.5 squared times 2, we get 0.05 or 500 times 10 to the minus 3 kilogram meters squared. So this is what, like, I don't know how many times bigger, 25 times more inertia when it's out here than here. And if you could actually see this thing like in lab, you would see this is very easy to twist, and this is very difficult to twist. It has much more inertia. Okay, so that's how we can deal with point masses. Let me pause and come back. Okay, suppose we have a rod like a meter stick or a 1 meter rod, and it's not massless. It actually has some mass. And we drill a hole in the center and we want to spin it. Obviously, it has some inertia. And so how do we get the inertia of this? It's not a point. And since the axis is the center, and usually, like even these masses, right? If we were measure from the axis to this mass, where would you measure? You'd measure to the center. So if we consider the rod like a point at its center, then the distance from the axis to the rod is 0. We'd get 0 for inertia, so it makes no sense. So one of the ways to do this, in fact, the way to do it, is to cut the rod into pieces. So if I cut it into 2 pieces, let me pause the video. Okay, let me just say, if you're in Physics 101, this part may not be so important. If you're in Physics 111, this is very important. So I cut the rod into 2 pieces. So this is 1 piece. And so it's still not a point, right? But how am I going to deal with it? I'm going to consider it a point at this point. So I have a point mass of what? 50 grams at a distance. If this is a distance of 25 centimeters. So I'm going to treat this as if it's a point. It's not really a point, but I'm going to get something that's not 0. So here's a piece which is 50 grams, 50 centimeters away from the axis, and here's another piece. So we could calculate that. But if we were going to calculate it in a general sense, it would look like this. So yes, I want you to get used to doing general solutions. So rather than saying, oh, this is 50 grams, 25 centimeters away, we're going to say for any mass, this is m over 2. And the distance from the center of that piece to the rod is L over 4, but we have to square that. So this you can calculate, and you're going to get I equals... Well, I'm not going to do it because it's part of the homework problem. And you're going to get a result. Okay. But the result is going to be a little bit weak. So let's make it better. How do we make it better? We make it better by making the pieces smaller. So now the pieces start to get smaller, right? So now we have 2 pieces. What's the mass of those? That's m over 4, m over 4, m over 4, m over 4. What's the distance to this piece? Well, it's L over, what is that, 1/8 of the rod, right? Because that's 1/4, so it's 1/8. So m over 2, L over 8 squared, and there's 2 of them. And then you have m over 2, but these are further out. What's that distance? Well, that's 3/8, right? This would be 1/2. So that distance is 3/8. So you have 2 of those, m over 2, 3/8 L squared. You say, this sounds messy. It's not so bad. And you're going to have to do it in the assignment problem. So anyway, how do we go even further? Well, we make more pieces. How many pieces should we make? We've got 2, 4, 8, 16, 32. How about make an infinite number of pieces? In this case, we get I by integrating all the infinite number of pieces, right? So we cut this into a little dx, and that little dx has a certain amount of mass we call dm. And so for every little dm, we measure its distance from the center, and we integrate all of them. If you're in Calc 2, you should be able to do this. If you're in Calc 1, it's a good time to understand that the integral is an infinite summation, and you'll get to see this when you do the problem in the assignment this week. So for things that aren't point charges, we need to use calculus to get them. And what we end up with when we do that for the rod is we end up with the equation that for Physics 1 people you'll just be given, and for Physics 111 people you'll be given, but you know how to get it. And so I for a rod is 1/12 ml squared. Where does that come from? That comes from the calculus. And there will be other equations for other forms, like what's the rotational inertia of a disk or a hollow sphere, and so on. So there's a whole table of values of rotational inertia for all these different objects, and in most cases we'll just look them up in the table. Okay, one more thing, and then you'll be ready for the entire assignment. So back to our rod. We have this rod, and we use calculus to find out that the rotational inertia of a rod is 1/12 ml squared. So as long as we know the mass and the length, we can calculate its rotational inertia. But that's done with the axis through the center. So supposing we take this stick, this rod, and rather than putting our hand at the center and twisting it back and forth, supposing we grab it at the end and we twist it this way with the axis through the end. Think about it. It's going to have more inertia. It's going to be more difficult to twist. So the axis is also important. So how do we get the inertia of this rod, knowing where the axis is and knowing what the inertia of the rod is with the axis through the center? We have something called the parallel axis theorem. Okay, this is for everybody, Physics 101 too. The parallel axis theorem says that if you want the inertia of the rod where the axis is not at the center of mass, the center of the rod, you need to add the inertia about the center, that would be the 1/12 ml squared. You need to add to that the mass of the rod times the distance that you move the axis. In other words, in this case, if we wanted to do this, supposing this is 100 grams and 100 centimeters, we could use this equation to calculate the rotational inertia about its center. We would have to add the 100 grams plus the distance we move the axis, in this case 50 centimeters, whatever that distance is, from the center of mass to where the axis is. And so you're adding that, that's the increase in inertia. And so this parallel axis theorem allows us to deal with any wide variety of situations where the axis is not through the center of mass of the object. Okay, you're ready for assignment 11 and lab 11. Go to it.